We have defined lots of nomenclature, words, and so on for stochastic process, but ultimately our objective is to be able to manipulate random processes like add two samples and so on. And lots of those manipulations you can do it based on whatever you have learned on just random variables and multiple random variables and so on, because you take samples and you do it. However, one of them manipulation is integration. Integration is nothing more than summation. So in this video, we will look at integration of one random process. Suppose that S of t to be integral of your random process over interval of a to time t. So this should be a small t and so on. In this case, we can calculate expected value of S of t very easily, because we have expected value of an integral from a to time t, x of 2 time d2. Remember that here we have time t, and this is why I have to use, and this is a dummy variable of integral. So this dummy variable of integral should be always different with the boundary of the integral. So these two. Okay, so because I want it to be a function of t time t is used here, I cannot use the same dummy variable. So I always do that. So this is what I need. Remember that this expectation is equal to integral over the distribution. If I have two random variables, it's going to be double integral, more random variables, and so on. And then I have an integral from a, this guy, from a to time t, x of time 2, d times 2, and then here you put the PDFs and then the variables of the integral. Obviously, you could change the order of these integrals with this distribution because the boundaries of this distribution and the boundary of this integral are different. So this will become integral. So I put this integral outside. Integral from a to time t of expected value of x of 2. This expected value is just this integral over distribution. So expected value just means integral over distribution. So it's abbreviation of integral over distribution. So this goes there, and then you will have d of 2. So always when I see these integrals, so I don't need to think about these middle stuff, okay? So I just erase it in my mind, and then I don't look at it. So I simplify this one, and I go to the end. I change the order of this integral and this integral. So the expected value of this random process gives me, the integral of the expected random process gives me. So what it means that if I give x of t to a system which does the integration over a to time t, it gives me s of t. This is a system. Now, if I give expected value of x of t to the same system, it gives me expected value of s of t. The reason is that I see the same expression. I just replaced x of t with here. These two expressions, this one and this one, are same. Just I replace x of t by the expected value. So if you give expected value to the same system, gives you expected. So always expected value of the output of an integral is the output of the system when the input is the expected value for an. Similarly, if I want to calculate cross correlation of two samples of my random process, I will take a sample at this one at time t1. So expected value of this guy s at time t1. And then this is at time t2. If they are complex conjugate, I put a conjugate on top of that. If not, I don't need to put. If it is not complex random variable, and if you put conjugate, you won't harm. So this is why you could put always here, and no mistake is going to happen. And this is why programming languages usually they put the conjugate in the prime operation, which is simpler, Phython, MATLAB, and so on. So then I replace these guys by S of T1. So I put here, instead of this T, I put T1, and then instead of this is S of T1, and this is S of T2. And then I put a conjugate. Conjugate goes inside the integral. I get this one. So remember that this expectation is one integral. This is another integral. I made sure that I use a different dummy variable. So this new here is the dummy variable of this integral. If these two dummy variables are same, if I put 2 here, then I cannot merge these two integrals. So I put them differently. So these double integral will become these two integrals, separate integral, because this is one separate integral, this is another one. So I make it a double integral, and then I have x of 2, x conjugate of nu, because the dummy variables are different, d2, d nu. One integral is over 2, the other integral is over nu, and both of them start from a to t1, and the second one is start from a to time t2. And now I have another expected value, which is an integral. I could change the order of this double inner integral and this expectation, which is outer integral. But remember that this may be not just one integral, it's lots of integral. Change the order, and then you get the expected value of this one instead of that. So you can change the order of integral, you get this one. And obviously this is equal to Rx x at time 2 and time nu. Because if you take a sample of this random process at time t2, you get this one. And if you take a sample of this one at time nu and put a conjugate, you get this one. So what I get is that a double integral of the autocorrelation of the input gives you the autocorrelation of the output. Similarly, you can get autocovariance of the output in terms of the autocovariance of the input, and it's going to be same. So here you put autocovariance of the input. So this simple system, the second order moments of the output, can be written and expressed in terms of the first and second order moments of the input very easily.